Let us now continue our discussion on the chapter of circles and chords inside the circles. We have seen previously two theorems. We will continue now and discuss a couple more theorems and their converses. So the third theorem that we are going to see is stated as follows. The perpendicular from the center of a circle to a chord bisects the chord. So that means if we have a chord AB, the perpendicular line from the center of the circle to the chord bisects the chord. That means it divides the chord into two equal parts. That is, AM will be equal to BM if OM is perpendicular to AB. So in this statement we are given that the line from the center of the circle to the chord is perpendicular to the chord. That is, OM is perpendicular to AB, and we have to prove that this line bisects the chord. That is, we have to prove that AM equals BM. To make this proof, the first part of construction that we will do is we will join OA and OB. So we will join the point OA, the points O and A. So we have this line OA, and we will also join OB. So we have this OB line also shown in the dotted lines in pink. Now, in this triangle AOB, okay, in this big triangle AOB, we notice for the two things, okay. The first thing we notice is that OA is equal to OB because both OA and OB are the radii of the circle. OA is the radius of the circle and OB is also a radius of the circle. So the radius of the circle must be the same at any point. So therefore OA is equal to OB. That's the first observation we make. Now that we have OA equals OB, it means that the triangle AOB is an isosceles triangle. And we know from our discussion on triangles before that, in an isosceles triangle, the angles opposite to the equal sides are also equal. So that means angle OAM must be equal to angle OBM. So that means this angle OAM is equal to the angle OBM. Okay, so this is from the isosceles triangle property. And we also know that since OM is perpendicular to AB, the angle OMA and the angle OMB are both 90 degrees. So that means we have this as 90 degrees and this as 90 degrees as well, which is what we have stated here. Angle OMA equals angle OMB equals 90 degrees because the line from the center of the circle to the chord is perpendicular to the chord. That is given to us. Okay. Now with this piece of information, let us now look at the two triangles AOM and the triangle BOM and check for their congruence. So in these two triangles, we have angle OMA is equal to angle OMB equals 90 degrees. Angle OMA equals angle OMB equals 90 degrees. So that means these two triangles are right angle triangles. And then we have the hypotenuse of these two triangles are equal. So the sides OA and OB are the hypotenuses of each of these two triangles. So OA equals OB is the hypotenuse. OA equals OB. Okay, they are the hypotenuses of the two triangles. And we have one of the sides as a common side, which is for both the triangles OM equals OM. That's the common side. So therefore in these two triangles, so we have in these two triangles AOM and BOM, one of the angles is 90 degrees. The side OA and the side OB are the hypotenuses of the two triangles. So we have a right angle, we have a hypotenuse, and a common side which is equal to both the triangles, okay, which is a common for both the triangles. Therefore, by the RHS congruence, we can say that the triangles AOM and the triangle BOM are congruent to each other. Now that we have shown that the two triangles AOM and triangle BOM are congruent to each other, we can now apply the CPCT rule and show that the corresponding parts of the congruent triangles are equal. So by CPCT we can show that the side AM of the triangle AOM is equal to the side BM of the triangle BOM. So we will show now that by CPCT side AM is equal to side BM. That means the perpendicular OM is dividing AB into two equal parts. That means the perpendicular from the center of the circle to the chord is bisecting the chord. Okay, so we'll write that. So that means that since AM is equal to BM is proved, it means that the line OM from the center of the circle to the chord AB bisects that chord AB. Hence we have proved the theorem which says that the perpendicular from the center of a circle to the chord bisects the chord. Next we will see the converse of this theorem, which will state that the line drawn from the center of a circle to bisect the chord is perpendicular to the chord. So in that case it is given that the line from OM is bisecting the chord AB. That means what is given to us is AM is equal to BM, and we have to prove that this line OM is perpendicular to AB. So we have to prove OM is perpendicular to AB. In other words, we have to show that the angle OMA and the angle OMB are both equal to 90 degrees. This is the converse of the previous theorem. So let us look at the two triangles OAM, which is this triangle on the left, and the triangle OBM, the triangle on the right, and check for their dimensions. So the first thing we notice is that the OA is equal to OB because they are the radii of the circle. OA equals OB radii. Okay. The next thing we know is that AM is equal to PM. This is given to us. This is given in the statement because the OM is given to be bisecting the chord AB. So AM is equal to BM is given. And we also have the common side OM. So OM is common to both the triangles. So OM equals OM. That's the common side. So now we have three sides of the two triangles matching each other. So by the SSS congruence, by SSS side congruence, we have that triangle OAM is congruent to triangle OBM. Now we can apply the CPCT rule and show that the angle OMA is equal to OMB. By CPCT, we can state that by CPCT, corresponding parts of the congruent triangles, angle OMA is equal to angle OMB. Okay, so the first thing we have shown here is that the angle OMA is equal to OMB, but we have not yet shown that these are equal to 90 degrees. For that, what we notice is that OMA and OMB are a linear pair of angles, therefore their sum is 90 degrees also. So we notice that also angle OMA angle and angle OMB are linear pair. So therefore angle OMA plus angle OMB should be equal to 180 degrees. But we know from the previous statement here that OMA is equal to OMB. So if both are equal, then both must be equal to 90 degrees. So 90 plus 90 will be 180 degrees. So if I can call this as 1, so we can write from 1, we can write 90 plus 90 equals 180 degrees. So OMA plus OMB, the sum of these two triangles are 180 degrees because they are or the sum of these two angles is 180 degrees because they are a linear pair of angles. And we also have that these two angles are equal to each other, so therefore they should both be 90 degrees. So hence we have proven that So you can say that angle OMA equals angle OMB equals 90 degrees. That is OM is perpendicular to AB, which is what we had to prove. Okay, we were given that the line OM bisects the chord AB, so therefore AM equal to BM was given to us, and we had to prove that OM is perpendicular to AB, which is what we have proved here. Since we get OMA, which is this angle here, and OMB, which is this angle here, are both 90 degrees. So this is perpendicular and this is also perpendicular. So we have OM perpendicular to AB. Hence we have proved this converse of the previous theorem as well. Let us now look at the next theorem related to the chords. The next theorem states that the equal chords of a circle are equidistant from the center. So if we have two chords A, B and C, D, and if these two chords are equal in length, then their distance from the center of the circle is also equal. So in this case, what we are given is that the lengths of the chords are equal. So AB equals CD is given to us, and we are also given that OM and ON are perpendicular to AB and CD respectively. So OM is perpendicular to AB because the distance of the chord to a point is the perpendicular line between the chord and the point. So OM is perpendicular to AB, and similarly ON is perpendicular to CD. So this is given to us, and we have to prove that the lines OM and ON are equal. That means the distance of the chords from the center are equal. Since the chords are equal in length, their distances from the center of the circle are also equal. So that is what we have to prove. To prove this theorem, let us see what information we have available at hand. The first point we notice is that since we have OM perpendicular to AB, from the previous theorem we know that the perpendicular from the center of the circle to a chord bisects the chord. Therefore AM is equal to BM. We have this observation here. And similarly, since ON is perpendicular to CD, ON bisects CD. Therefore CN is also equal to DN. And we also know from the starting point that AB is equal to CD, and since AB is equal to CD, half of AB and CD will also be equal to each other. So therefore we have AM equals BM equals CN equals DN. So that means each of these line segments, AM, BM, CN and DN, they are all equal to each other. So AM equals BM equals CN equals DN. So we have these four line segments equal to each other. So this is the first piece of information we have. The next thing we would do is we would join the points O and B. So we have OB joined here, and we also join the points O and D. Okay, now we will notice that OB is equal to OD because OB and OD are both radii of the circle. And we can make this observation in our triangles OMB and OND. So let's look at these two triangles OMB and OND and check for their congruence, and there, using that congruence, we can go on to prove that OM is equal to ON, which is what we started off to prove. So we have in these two triangles, triangle OMB and triangle OND, the first observation is that the angle OMB is 90 degrees since OM is perpendicular to AB, and also ON is perpendicular to CD, therefore OND is also 90 degrees. So we have these two triangles, triangle OMB and OND are now right angle triangles. So we have one of the angles is right angles. Then we have the hypotenuse side, which is equal. So OB and OD, which are the radii of the circle, are also the hypotenuses of those two triangles. So they are equal. And finally, we have the side BM of this triangle OMB and the side DN of the triangle OND also equal, as we have seen here. BM is equal to DN. So BM, which is this line here, this side of the triangle, and DN, which is this side of the triangle, are also equal. BM equal to DN, as we have shown earlier here. So we have the third side also equal. BM equals DN as we have shown earlier. So we have a right angle, we have a hypotenuse, and we have a side. So we have RHS congruence available here. So by RHS congruence we can show that the triangle OMB and the triangle OND are congruent to each other. And since these two triangles are congruent to each other, we can go on to show that OM is equal to ON by corresponding parts of the congruent triangle. So by CPCT we can show that OM is equal to ON, which is what we had to prove. OM equals to ON. So if OM is equal to ON, it means that the chords AB and CD have the same distance from the center of the circle, which is what the theorem states. Equal chords of a circle are equidistant from the center of the circle. So by CPCT we can show that OM is equal to ON, and therefore the equal chords of a circle are equidistant from the center. So in this way we have shown that OM equal to ON, and therefore the chords AB and CD are equidistant from the center O. Okay, so we started off with the chords having equal length, and we have shown that the chords have equal distance from the center of the circle, which is what the theorem states. Let us now do the converse of this theorem, where it will be given that the chords are equidistant from the center, and we have to prove that the chords are of equal length. So that will be the converse of this particular theorem, which says that the chords equidistant from the center of the circle are equal in length. Okay, in this case we are given that the distance from the center of the circle to the chord is equal, that is OM equal to ON is given to us, and we have to prove that AB is equal to CD. Okay, and since we measure the distance from a point to a line in the form of a perpendicular line, we also have this information that OM is perpendicular to AB and ON is perpendicular to CD. And with this information, that OM and ON are equal and OM and ON are perpendicular to the chords AB and CD respectively, we have to prove that the chords are of equal length. That is, we have to prove that the chord AB is equal to the chord CD. So to prove this, we will, as before, join the points O and B and the points O and D as well. Okay, and now we have these two triangles, triangle OMB and the triangle OND as before, and using this we will show the congruence of these two triangles, and from there we will proceed to show that AB and CD are equal. Okay, so the first piece of information we have is that OM is equal to ON is given to us. So we have OM equals ON, and that is given. And we also know that the angle OMB is equal to the angle OND, and they are both equal to 90 degrees because the distance from the center of the circle to the chord is measured by the perpendicular line between the chord and the center of the circle. So therefore, since it's perpendicular, we have this angle and this angle to be 90 degrees. And then we have OB equal to OD. So we have OB equals OD because they are the radii of the circle. They both are the radii. So now we have three dimensions of the two triangles matching each other. We have one side matching each other. We have one pair of angles matching each other, and those angles are equal to 90 degrees. So that means it's a right angle. And we have a side, and we have the radii part, which happens to be the hypotenuse of this right angle triangle. So the radii is the hypotenuse. Okay, so we have a right angle, a hypotenuse, and a side. So we can apply the RHS congruence rule to show that the triangles OMB and OND are congruent to each other. So now that we have the two triangles OMB and OND congruent to each other, we can apply CPCT to show that the side BM is equal to the side DN. So by CPCT we will have BM equals DN. So that means we have this line BM is equal to the line DN, and we also know that since OM is perpendicular to AB, OM bisects AB, so that means we can say that AB is 2 times BM. So we have AB equals 2 times BM since OM bisects the chord AB. Similarly, since ON bisects the chord CD, we can have CD as 2 times DN as well. So we now have these two expressions. The chord AB is 2 times BM and the chord CD is 2 times DN. And since BM is equal to DN, 2 times BM is also equal to 2 times DN. So therefore we can say that AB is equal to CD since BM equals DN. So therefore AB, which is 2 times BM, and CD, which is 2 times DN, they both must be also equal since BM is equal to DN. So therefore AB equals to CD, which is what we have to prove. If the chords are equidistant from the center of the circle, then the chords are equal in length, which is what we have proven here. We have proven that the length of the chord AB is equal to the length of the chord CD. So AB equals CD, which is what we set out to prove. So this proves the fourth theorem as well, which is the converse of the previous theorem. So we have in the previous theorem, equal chords of a circle are equidistant from the center, and the converse of the theorem is that if the chords are equidistant from the center, then they are equal in length, and we have proved that as well. Okay, we will stop here for this lecture, and we will continue with the next set of theorems and proofs in the following